Welcome back to my YouTube channel of the subject Basic Electrical Engineering. In this video lecture series, we have started one chapter that is three-phase AC circuits. And in three-phase AC circuit, we have seen that how the three-phase voltage is generated and what is the importance of that three-phase voltage. In today's video, we are going to study about interconnection of that three-phase system with the three-phase load. So basically our three-phase system is having three terminals and that we have studied as red, yellow and blue. So this three terminal should be connected with the three terminals of the load. But whenever we are connecting a single phase terminal to any type of instrument, then there is a written path and which is known as the neutral path. So if R is having a neutral path, if Y is having a neutral path and if B is having a neutral path, then there is a 6 conductors. And there is also 6 terminals of the load. So it is quite complex process to connect 6 voltages, 6 terminals of the system to the 6 terminals of the load. So that's why we need to define some modern technology to connect this three-phase system to the three-phase load. And that interconnection are known as the star connection and the delta connection. So in today's video, I am going to explain you the three-phase star connection. But before starting with the star connection, let's discuss some important definition, important terms related to this three-phase system. First important term is the balanced load. So what do you mean by balanced load? We are having a three-phase system and we are having a three-phase load. We have seen in the earlier video that if our coil is having the equal number of turns and equal phase difference between each other, then they produce the same magnitude of voltage. So in the same manner, balanced load means the impedance of each phase is same, then it is known as the balanced load. That means the current flowing through each phase of the load will be same. The voltage across each phase of the load is same, but it must have the same amount of impedance. Next is the unbalanced load. So the unbalanced load means load that has different or not equal impedance. So they are not having the equal magnitude of impedance. Third definition is the balanced phase voltage. That I have already told you, balanced phase voltage is having the equal magnitude in all three phases and the equal phase difference between all that three phases, and that equal phase difference is nothing but the 120 degree. So we can say that this is a balanced phase voltage in load or a system. Fourth definition is balanced phase current, and this is also having the same definition as if our phase current in all three phases is having equal magnitude and the phase difference between all that three currents are equal, then it is known as the balanced phase voltage. So this was the very important terms that we are going to often use in this star and delta connection. So now let's introduce the types of connection we can make to connect the three-phase system to the three-phase load. And there are two important type of connection is star connection and the delta connection. So each of this connection is differ in terms of relationship between voltage and current. In star connection, voltage and current relationship is different, and in delta connection, voltage and current relationship is different. So this connection is connected on the both side, on the load side also and on the source side also. So let's discuss first the star connection of three-phase system. So in star connection, the similar, because now we are having 3 coils and each coil is having 2 terminals. I have told you, one is the live terminal and another one is the neutral, or you can say the return terminal. So there are 2 terminals, or you can say that positive, negative, positive, negative, positive, negative. So each coil is having 2 terminals. So to make that 3 coils in star connection, what we have to do is we have to connect similar terminal of each coil together. So in the star connection, the similar ends, either starting end or the finishing end of the 3 windings should be connected together. and that common point is known as the neutral point. That connection which is made at the similar point, similar junction, and that point is known as the neutral point. And the three different, that was the dissimilar terminal, that three line conductors run from that terminals on. So line terminal, from that terminal on, again the coil 1 is connected at the neutral point and another terminal is work as a line terminal. Same for the second and same for the third. The wires carried to the external circuit giving three-phase, three-wire system. If three wires are taken out from that three coils, then this system is known as the three-phase, three-wire star-connected system. However, sometimes a fourth wire is also carried out from this star connection and that is nothing but the neutral wire. Then in that case, you can say that this is a three-phase, four-wire star-connected system. So if you are taking neutral also in this connection, then it is a four-wire system. And if you are not taking neutral in source to load connection, then it is a three-phase, three-wire system. So now let's see the diagram for this three-phase star connection. You can see this diagram. In this diagram, we have connected similar terminals together to this junction, and this junction is known as the neutral junction. Okay, and this wire is carried out from this is known as the neutral wire. This is the first line wire, that is A, this is the second line wire, that is B, and this is the third line wire, that is C. Or you can see this figure. In this figure, there are terminals named as A dash, B dash, and C dash. You can see that the similar terminal, that is A dash, is connected to B dash and B dash is connected to C dash. So you can see in this diagram, A dash, B dash and C dash is connected together and this forms a neutral point. And from this junction, we have taken neutral point out. Another three terminal which was not connected to that junction is taken as a line wire, that is A, B and C. So this is known as a star. Now let's see some important definition related to star connection. So in star connection, important definitions are: first is the phase voltage, which is treated as VPH or EPH. PH stands for the phase and V and E stands for the voltage. So the voltage measured between the neutral and any line, or you can say line to neutral. So any voltage which is measured between any line and neutral is known as the phase voltage. Second definition is the line voltage. The voltage measured between any two line of the system or the load is known as the line voltage. So you can say that line to line voltage. Phase voltage is the line to neutral voltage and line voltage is the line to line voltage. Third important definition is the phase current. Phase current is defined as the IPH, and the phase current is the current flowing through the each phase of the source of the load. So current flowing through the coil is known as the phase current, or you can say current flowing through the load, each phase is known as the phase current. Fourth definition is the line current. Current flowing through each line of the supply or the load is known as the line current. So we will see all these four parameters in next figure. So you can consider this figure here. We have connected three coils. We have taken previously A1 A2 coil, B1 B2 coil and C1 C2 coil. You can see here neutral terminal, and neutral terminal is connected at the similar terminal of this three coil is A2 B2 and C2. And this A1 B1 and C1 is treated as the line terminals. So a wire taken out from these three line terminals. So now let's discuss that four parameters in this figure. First parameter was the phase voltage EPH, and the definition was the voltage measured between each line and neutral. So you can see here, this is first line and this is neutral. So the voltage across this coil is known as the phase voltage. Second was the line voltage. So voltage measured between any two lines is known as the line voltage. So you can see that this R and Y line and the voltage measured between these two lines is known as the line voltage. Third definition was the phase current. So the current flowing through each phase of these three coils or the load is known as the phase current. So this is the phase current. And the line current is current flowing through each line is known as the line current. So this is line current. So the four important definitions that we have discussed earlier is shown in this figure. Now let's discuss the relationship between voltages. Which voltages? Phase voltage and line voltage in star connection. So if you want to define the relationship between voltage and current, then you have to consider this figure. In this figure, there are three coils, R coil, Y coil and B coil, and there is a neutral terminal taken out here. So this is a R line, this is a Y line, this is a neutral line, and this is a B line. R, Y, B, and this is a neutral line. Now let's define all the parameters in this diagram only. So first let's define the phase voltages. So the voltage measured between R and neutral is the phase voltage of the R coil, that is ERN. This is EYN is the phase voltage of second coil, and this EBN is the phase voltage of this third coil, that is the B coil. Now let's define the line voltage, line to line voltage. So the voltage between R and Y line is VRY, the voltage between Y and B line is VYB, and the voltage between B and R line is VBR. So VRY, VYB and VBR are the three line voltages. Now let's define the phase current. So the current flowing through this first coil is IR, current flowing through this second coil is IY, and the current flowing through this third coil is IB. So these three currents are known as the phase current. Now let's define the line current. So the current flowing through the first line is written as IL1, IL2 and IL3 are the current flowing through the three different lines, that is R, Y and B. So this IL1, IL2 and IL3 is known as the line current. And neutral is not having any type of current because zero current will pass through this neutral. Now, please understand that these three phase voltages are equal in magnitude and apart 120 degree from each other. So now let's start deriving the voltage phase relationship between phase voltage and line voltage. But before starting the relationship between phase voltage and line voltage, let's first talk about the phase current and line current. Why? Because you have seen in previous figure that the phase current which is flowing through the coil is the same as the line current. So from this figure, you can see that the current flowing through each phase is the same as the current flowing through each line. So IR is equals to IL1, IY is equals to IL2 and IB is equals to IL3. So basically we can say that there is no relationship between phase current and line current, they are equal in amount. So IR, if we are talking about the balanced system, then all the phase current are equal in magnitude, as IR is equals to IY is equals to IB is equals to I phase, or you can say IL, where IR is the current of R phase, IY is the current of Y phase and IB is the current of B phase. So you can say that IR is equals to IY is equals to IB is equals to line current, or you can say phase current, because in star connection there is no relationship between line current and phase current, they are equal in amount. So we have talked about the current. Now let's talk about the voltage. So to find the relationship between line voltage and phase voltage, we must have to draw the vector diagram. From the vector diagram only we can find the relationship between line voltage and the phase voltage. So you can see this vector diagram. In this vector diagram, first you have to draw three lines. Which three lines? The three phase voltages. And we know that three phase voltages are 120 degree apart from each other. So here you can see that first we have drawn the voltage of Rn, that is the voltage of R phase ERN. 120 degree apart from this voltage, we have drawn the another voltage of the Y phase, that is EYN. And 120 degree apart from this, we have drawn the phase voltage of B phase, that is EBN. So first we will draw ERN, EYN and EBN, and these three are 120 degree apart from each other. Now let's consider the same diagram that we have discussed earlier. So in this diagram, you can see that the line voltage, that is the voltage between R and Y line, that is VRY, is the phasor addition of ERN and EY. But you can see the direction of current flowing through these two coils. Direction of current flowing through these two coils is different. So we have to do phasor difference. That is ERN and EYN, one of them should be taken in negative to find the resultant voltage, that is the line voltage. So we can say that any line voltage in star connection is the phasor difference of two phase voltages. So now let's back to the vector diagram. So in this vector diagram, we have drawn Rn, we have drawn Yn, and we have drawn Bn. Now what we have to do is, we have to do phasor difference. So the first voltage, that is the line voltage between R and Y coil VRY, is nothing but the phasor difference of Rn, that is the phase voltage of R coil, and the phase voltage of Y coil. And we have reversed the phase voltage of Y coil. So if EYN is drawn here, then the reversed vector, that is in negative vector, is drawn here. If this vector is reversed, then the angle, the total angle was 120 degree, but now this vector is reversed, so this angle will be 60 degree. So basically now we have to add this ERN and negative of this vector, that is EYN. So ERN, EYN should be added. So by parallelogram method, this vector should be drawn here, and this vector with the same angle should be drawn here, and the intersecting point is our parallelogram, and the diagonal of this parallelogram is our resultant voltage. So this ERN and EYN is added, and we obtain the phase the line voltage VRY, and which makes 30 degree with each of this voltage. And similarly, to find the line voltage YB, that is the line voltage between Y and B line, then you have to add the B and negative, or you have to add the phase voltage of Y and negative of B. And if you want to find the line voltage, that is VBR, then you have to take B as a positive and R as a negative. So by parallelogram, you can also find. Now let's focus on this first parallelogram only. So if we are doing mathematical operation to find the diagonal's magnitude, then we can obtain the relationship between line voltage and phase voltage. So let's derive the relationship between line voltage and phase voltage. So in a balanced star system, first, the magnitude of phase voltage in each phase is same, V phase, because all phase voltages are having the equal magnitude. So that means ERN is equals to EYN is equals to EBN is equals to V phase, or you can say E phase. So from the vector diagram, we have clearly seen that the any line voltage is the phasor difference of the two phase voltages, and similarly for another two vectors also that we have already discussed. Now, as the angle between ERN and EYN was 120 degree, but we have reversed the EYN vector, so that is minus EYN. So the angle between them will be 180 minus 120, that is 60 degree. This is also we have discussed. So if you want to find the magnitude of the line voltage VL, or you can say the diagonal's magnitude, then you have to use the triangular property. That is the side square, that is ERN square, plus another side square, that is EYN square, plus 2 times ERN EYN into cos 60. Because the total angle between these two lines is 60 degree. So ERN and EYN is treated as the phase voltage only, because they are having the same magnitude. So here we will put E phase, here also we will put E phase, here also we will put E phase. So it will be E phase square plus E phase square plus 2 times E phase into E phase, and the value of cos 60 is nothing but the 1 by 2. So this 2 will be cancelled out, and this E phase and E phase is treated as E phase square. So we have equation as under root line voltage is equals to under root E phase square plus E phase square plus E phase square. So it will be under root 3 times E phase square. So if we are giving square root to both this term, then it will be root 3 and in under root E phase square. So if we are removing under root from the second term, then it will be root 3 times E phase, or you can say root 3 times V phase. And the value is this root 3 V phase is the value of the line voltage. So we can say that the line voltage in star connection is root 3 times the phase voltage. So for star connected system, we can say that line voltage is equals to root 3 times the phase voltage, and line current is equals to the phase current. So this is the relationship between voltage and current in star connected system. Now let's discuss the last point, that is the power in this three-phase system. So as the angle between the phase voltage and the phase current is 5 degree, so the electric power per phase, means power in only one phase, is given by this formula. phase voltage, phase current, and cosine of the angle between them. So this is the basic formula for the power in each phase. So if you want to put this quantity in line terms, then V phase is equals to VL by root 3, I phase is equals to IL, and cos phi will be as it is. So this is also known as the power per phase. But if you want to find the total power of the entire three-phase system, then you have to multiply 3 with this equation. Either you can multiply 3 here or you can multiply 3 here. So if we are multiplying 3 in the line equation, then it will be 3 times VL by root 3 into IL into cos phi. So this root 3 will be cancelled out and only root 3 will appear in numerator. So it will be root 3 VL IL cos phi. So please remember this equation in three-phase system, three-phase star connected system, the power consumed by the entire three-phase system is given by this formula, that is root 3 VL IL cos phi. So this was all about the star connected system. Thanks for watching this video. Stay tuned.